we've got Carlo Luschi, who's Director of Research at Graphcore. Really excited to see what he has to present. And over to you, Carlo. It's a pleasure to have you.
Thanks very much, Nathan. The presentation is on processing for machine intelligence. And this is a short summary of the few topics that we will be covering. We start with an introduction of the IPU architecture. And then a numerical representation, low precision format are becoming more and more important as a way to improve the computational and memory efficiency of hardware platforms. And then I'll go through some of the topics that we are working on at Graphcore Research to support the algorithmic innovation for delivering hardware efficiency and algorithmic efficiency for AI. The goal for us is to support the community to support the ultimate computational platform for machine intelligence. So the IPU architecture is based on a completely new perspective on what is silicon efficiency. Basically, the current situation with silicon technology is that at each process node, it's no more possible to double the transistor logic, the processing logic, maintaining constant the power. So doubling the transistor logic is still possible, but the power goes up. So that implies that the silicon efficiency is really being able to use all the available power all of the time. And to do this, given a certain die size, going ahead would no more be possible to power up the same percentage of the die. Going towards a higher transistor density will be going towards being able to power up a smaller and smaller portion of the chip. And so what we advocate is to fill the rest of the chip with memory, which consumes less power. So the proposition is to have memory on chip that has the advantage of being close to the compute so that the access consumes less power and is quicker. Also, in our first generation of the chip, the memory is distributed. So we have a significantly high number of independent processors on the chip, each one with their own co-located memory. And then the other crucial thing, which I'll go into the details in a second, is the serialization of compute and communication. And then all this setup is based on the fact that the memory on chip supports storing the entire model that one needs to train on the chip. If the model is larger than the memory available on one chip, there are several techniques that we will go through in a minute, but in principle, it's always possible, and it's necessary nowadays with the over-parameterized models that are becoming prevalent. It's possible to use multiple chip cluster to store all the memory required for each one individual model. So, as I was saying before, our IPU, our first intelligent processing unit, our first version of our architecture, has a massive number of independent processor tiles. So each processor tile is one compute unit with its own co-located memory. And we have on the current IPUs, we have 1,216 processors with the memory that sums up to 300 megabytes per chip, 600 megabytes for each pairs of chip. And the other crucial aspect that I was addressing before is how, to make things efficient, we have chosen to support bulk synchronous parallel modeling. So to serialize communication and compute. So the rationale behind this is that doing parallel computing, having simultaneous compute and communication, it doesn't really tie with this principle of trying to use all the available power all of the time. If one designs, like in the left upper corner of the figure, if one designs things with parallel compute and exchange and communication to hit the power ceiling for a certain design point, and the operating point differs from what one has designed for, the consequence is that one risk of not using all the available power. Where serializing communication and compute, if the plan it doesn't match the instantaneous operating point, this implies simply that there is a saving of time, which actually is advantageous because one can start the following operation sooner. So that's really, these are the basic principles of the IPU processor. And this is just a detail of all the additional important aspects. I mean, this is the picture of the 1,216 IPU tiles, each one having an IPU core processor and the in-processor memory that I was describing before, and also there is provision for clustering together multiple units through IPU links, which are high bandwidth communication links among chips. Now, to support efficient compute and in terms of power, to support the possibility of running more computation with the same power, not only to speed up the compute, is essential to have an efficient numerical representation. So initially, until a few years back, Float32 was really the only option. But since a few years already, people have started to identify high precision formats as a viable option. And of course, our first implementation supports mixed precision Float16. We support the IEEE Float16. There have been other alternative Float16 format, the Google bfloat, which has the advantage of having the same number of exponent range of a Float32, but has a disadvantage of having less mantissa bits. And we'll see what this implies in practice in a second. And then, of course, going forward, there is now is the right moment not only to agree about on what is the most important, the number of Float16 formats that are relevant for the community to support, but it's the right time to agree what are even more efficient formats that we can use. Like Float8, this is an example of 152, 1 bit of sign, 5 bits of exponent, and 2 bits of mantissa, which is one of the most common choice from the experimental evidence that it's available in this moment. So what is the mixed precision arithmetic? Mixed precision, as is supported in our chip, is really having multiplying accumulation operation with lower precision inputs, in this case, Float16 input and higher precision accumulation, Float32, but then Float16 is used for storage after the accumulation is complete. This is quite efficient and has been proved to be giving state-of-the-art performance. This is just an example for a convolutional network where activations, weights, and gradients are all quantized with this mixed precision. So all the inputs, weights, and activation during the forward pass and weights, activation, and gradients during the backward pass are all Float16. And the accumulation is done on Float32. And even the weight update accumulation in this figure is on Float32. And one can appreciate that there is no any difference, and even gathering multiple runs and gathering proper statistical measures of the characterization of the performance, there is no difference, no significant difference between Float32, Float16, and bfloat. So one advantage of the bfloat for the gradient quantization is that the bfloat has so vast exponent range, even more than is necessary, that doesn't require any particular tricks to make a quantization of the gradient robust, where Float16 requires a technique that is called loss scaling, which has been proposed by NVIDIA a few years back, and it's quite robust. There are a number of automatic ways of implementing loss scaling, and we have been working on making even more robust for RNN and sequence input models. But then what happens if one uses a low precision format for the quantization of the weight update accumulator? So in this figure, all the remaining operations are quantized as in the previous slide, but the accumulator itself of the update of the weight performed by SGD, it's either Float32 or Float16 at IEEE or a bfloat format, quantized at every single update. So the problem with the bfloat in this case, they're both failing. Both the Float16 and the bfloat are failing. The bfloat is worse because it has less bits of mantissa. But then applying stochastic rounding every time one does the weight update accumulation, the IEEE Float16 recovers completely the performance, where the bfloat remains with a few percentage of degradation. So there is a trade-off. The other comment that is fair to make is that going towards mixed precision with Float8 inputs, to have 8-bit inputs for activation gradients and weights, both in the forward and backward pass, with Float16 in this case accumulation, there is a need of loss scaling anyway. So the previous discussion of the advantage of the bfloat with respect to not needing loss scaling then disappears in this context. So besides efficient numerical format, one immediate drive towards more effective computation, more effective training for any hardware platform are the techniques that reduce the memory requirement of training. Activation recomputation is a trade-off between compute and memory, And small batch training also reduces the memory requirement and allows, on top of that, to achieve better generalization performance. Very quickly, what is activation recomputation? Normally, with backpropagation, during the forward pass, one needs to store all the activations at the output of each layer. And these activations then are used in the backward pass progressively to compute the gradient of the loss with respect to the activations, to then having the gradient of the loss with respect to the weights, to update the weights themselves. But this storage of the entire set of activation of the entire network implies a significant memory overhead. So the idea here is to trade off compute and memory requirement to store only a subset of the activations, only for a subset of layers, and to recompute the intermediate activation during the backward pass as they are needed. And this is quite efficient. One reason why it is efficient is that in the worst case, it will imply an increase of compute only about 25 to 30%, thanks to the fact that most of the compute is due to the backward pass, which is normally twice as costly as the forward pass. And normally, the advantages in terms of memory reduction are in the order of 5, even 8 times lower memory requirement for most of the modern deep network architectures. The other way to reduce the memory requirement that I just mentioned, using smaller batch, is fundamental in terms of effectiveness of stochastic gradient optimization. So it's been proved that the best generalization performance are achieved by using a smaller batch. Using large batch not only reduces the performance in terms of generalization, but also makes training much more problematic in terms of range of linear rates that can be used in a stable way. Of course, that technique that had been used, has been mentioned before, warm-up, which is a way that Facebook has proposed, that it improves performance significantly, but then it moves the boundary where things stop to work. And this brings to the other angle for which batch size is important. Of course, if it was only a question of using the certain batch for optimization on a single chip, there was no argument small batch is better. But the batch size has the advantage that allows to do data parallel training, distributing training over multiple processors to speed up training. And the trade-off there is that with some techniques has been made possible recently to have successful training up to thousands, batch size thousands. But the problem, again, as I was mentioning, that has only moved the boundary. And this is also depending on the particular architecture, on the particular data set. At some point, the linear scaling of the speed up that one can achieve by adding processors stop to be possible. And one reaches at different points for different architectures and different data sets, saturation regions after which there is no more benefit from further parallelism. So of course, the different ways of tackling the data parallel training approach, besides synchronous SGD, one can reduce the computational data communication requirement by doing local SGD, decentralized SGD with periodic averaging or decentralized averaging. Of course, these are data parallel approaches that are speeding up training, sharing the load of gradient computation over multiple chips. The other techniques that are becoming more and more common are to use model parallel, that has been mentioned before again, and pipeline parallel, which allows, again, to split a model over a certain number of processors, but maintaining the efficiency of compute. And pipeline parallel, it's worth mentioning because, again, reuses the batch size dimension to make things more efficient. So it's another angle that exemplifies that there is a trade-off that we are trying to play. The conclusion, though, from our point of view, is that there is a place where we need to find different techniques that will improve the possibility of further parallelizing over thousands of workers. One technique that we have been studying, that has been proposed by several researchers over the last couple of years, is codistillation. This is just one of the techniques that are trying to decouple training of multiple models in parallel models without requiring for the models to be aligned with respect to the weights of the different models. So the co-distillation principle is having different networks that train kind of independently, with the only provision that the loss of each individual model, it has a component that penalizes prediction that are too different from the one of the other networks. This has several advantages. First of all, it requires to exchange only predictions instead of exchanging the weights, which has less communication, but also has the advantage that exchanging prediction is much less critical with respect to latency, which has been a big problem for exploiting synchronicity in SGD, in classical SGD training. The other interesting aspect of co-distillation is that has been shown that the advantage of having multiple model training in parallel is that this different training improve the diversity, improve the entropy of training. This is an example that we have obtained in our team, where the red curve exemplifies, again, co-distillation of a certain number of networks, but the only difference with the blue curve is that the co-distillation additional loss is introduced and not left constant, but is stepped up gradually during training. So to allow the different networks to maintain a certain independence for as long as possible during training, which has significantly improved performance. So another completely different but related, in a sense, angle to do distributed implementation is to resort to evolutionary computing. Evolution strategies in particular has achieved some renewed popularity over the last few years, but it's really a strong case of a technique that is very strong in terms of parallelization and reduced communication requirement. So basically, evolution strategies has a certain network that generates offsprings by randomly generating random permutations over a certain number of directions in the parameter space of the original network. And the interesting point is that these different permutations of the original network are trained completely independently on different workers. And this can be achieves the scaling, the parallelization of thousands of workers. The other advantage is that the only thing that at the end they need to communicate with each other to achieve the update of the parameters is an exchange of the fitness. So having generated random numbers over the number of offsprings that are generated for a single parent network, all these individual networks are trained independently and generate a fitness parameter that then is exchanged. And these fitness parameters are used to compute a weighted average of the random steps, random permutations that have been generated originally. And the weighted average achieves, like is shown in this figure, achieves an estimate of the gradient, which corresponds to a finite difference estimation over a random number of directions in the parameter space. So again, on parallelization, but not only, actually, the other great advantage of evolution strategies is that it's a black box optimizer. Doesn't rely on backpropagation, and which is also another direction that I think the community should continue to exploit. The other significant new direction in research that has become prevalent over the last year is the realization that training larger and larger over-parameterized models continues to deliver improved generalization performance beyond what was suggested by statistical learning. So statistical learning was suggested after a while, continuing to increase the number of parameters, one would overfit, where that doesn't seem really to happen with modern architecture. What this implies that at one point the computation required to training makes it impossible to go beyond. But has been shown together, the other observation is that it's been shown that at the end of the training of these massive models, only a minute percentage of weights at the end of training are different from zero, are significantly different from zero. So pruning the over-parameterized network at the end of training and reinitializing the network with only the small percentage of parameters that were not zero at the end has been proved to achieve, when retrained in isolation, not too different performance. There is some debate between different research groups recently. But there is a degree of evidence that it's possible to get to a similar order of magnitude of performance, only training a small percentage of those weights. And this is very attractive. Fixed sparsity pattern, of course, as what the evidence has suggested work, but what is even more attractive is the possibility of starting with a small network instead of a big network, and evolving the exploration of the parameter space periodically during training in order to maintain both the efficiency of training a small network, but also at the same time the exploration that is so rewarding in terms of achieving generalization performance as it is achieved by an overparameterized model. And in this respect, what will be really interesting, what we're trying to concentrate on, is if this process of exploration of the parameter space would reveal a structure of the sparsity that can potentially make even more efficient computation available. The final slide is on how overparameterized networks, the importance of overparameterized networks really has risen together with the use, more and more prevalent use of unsupervised training. Of course, the larger the network, the more and more there is a problem to find the amount of labeled data that allows training, and other unsupervised pre-training to then fine-tune to certain specific downstream tasks, or self-supervised learning, self-supervised training, have been proved to be very efficient in terms of making use of the huge amount of unlabeled data that are available today. And in particular, self-supervised learning has become a crucial point to enable model-based reinforcement learning, which has started to deliver really promising results for improving the sample efficiency of reinforcement learning agents. So this concludes the presentation. And the last slide I should put is that we are hiring in our research team, in Graphcore Research, both in London, Cambridge, and Bristol.